Hello, and welcome to the Lecture Review Series. My name is Brandon Young, and I'm your supplemental instructor for the semester. These videos are aimed at being a review of the week's lectures and will provide animations to visualize some of the concepts of thermodynamics. Let's get started. Thermodynamics is best described as the bridge between what we can see and what we cannot. It is the business of taking concepts like temperature, entropy, pressure, and surface tension and relating them to their origins from the world of atoms. To get a feel for this, we need to work our intuition for the magnitude of scale between these two worlds. How much of a difference is there? In class, we talked about how a joule is something macroscopic. You can feel a joule's worth of energy, much like when a frozen chicken is thrown at you at some mid-shopping brawl. But how much is 1 joule? How fast are things moving if they have 1 joule of kinetic energy? In terms of, say, a squirrel, it's pretty normal. It moves about 1 meter per second. That's about as fast as a normal squirrel just walking around. A human? It's actually pretty slow for a human, like a slow pace across a room. A flea? It's already insane for a tiny flea that you can barely see. If a flea had 1 joule of kinetic energy, it would move faster than Mach 4. So it's clear that atoms and molecules aren't in the business of dealing in 1 joule increments. In class, we walked through the derivation of the relationship between temperature and microscopic kinetic energy, Boltzmann constant. I'm going to go over this again. It is so vastly important to the worlds of both chemistry and physics that it might as well be put on a scroll to hold the weight of its importance. If you're going to memorize any equation and constant, this is the one you need for this class. We start with the fact that pressure is a force distributed over a given area. Recognize that molecules are small and constantly in motion. Therefore, any wall of a box full of gas is being constantly bombarded with small little atoms colliding against it. We can think of this force as a number of these atoms times the average force that the atoms exert over a long period of time. But how do we know what to put for this concept of an average force of all the atoms in a box over a long time? Well, let's go back to the world of Newton. He knew how things collided and moved on a macro scale, so that's as good as an approximation as any. Let's just think of atoms as bouncy balls for now. Also, let's just make this easy and consider only one dimension for now. His second law, F equals ma, should be familiar. Well, acceleration is just a change in velocity over a change in time, so we can replace that in. We also know that momentum is just mass times velocity, so now we can write that force is just the change in momentum over a change in time. Cool! Force is simply the change in something's momentum over the time that change occurred. Alright, so how does a particle's momentum change when it hits a wall? Well, let's see. If you hit a wall with a bouncy ball, it flies back in the opposite direction, so we take the initial momentum and subtract the final momentum of the ball. We get that the momentum changed by twice the initial momentum. This should make sense since the ball had to go from moving from one side to continuing to moving towards the other. If the change in momentum was 0, the ball would hit the wall and stop. So this can't be the right answer. Has one of you ever thrown a ball at a wall and it's stopped in place? I would bet never. Alright, back to our derivation. We know now that it's 2px here and we need to figure out the time aspect of the equation. Well, we know how big the box is, and if we know how fast the ball moves, we can find out how long it takes to hit the same wall. That'll just be twice the distance over its velocity, since we want to know how long it takes to hit the same wall. Remember, we are calculating the force exerted on one wall of this box. Now, we just have some simple algebra to do. Remember that momentum is mass times velocity, and we end up finding out that the force is equal to the mass times velocity in one direction squared over the length of our box. If we want the time average force, we just have to know the time average velocity since the other two variables are constant. This should look very suspiciously close to the kinetic energy equation, but notice we have only considered one direction. Now, here's a trick that sounds super fancy, but makes sense when you think about it. It is called the principle of equipartition. All it says is, hey, If energy can be distributed over various ways to move, it will be done so evenly. This is applied to the time average kinetic energy. So, if I'm a particle and I move in the x direction, I'm also equally likely to spend that energy moving in y and z. So over time, my average velocity is just the sum of all my individual x, y, and z components. Or, I could just as easily say it's just 3 times my x velocity. We can now plug this in and things start to look a lot more suspiciously like the kinetic energy equation. Usually kinetic energy has a 1/2, but right now all I have is a 1/3. Let's do a math trick and multiply by 2 over 2, which is just 1. Now, my time average force is equal to twice my kinetic energy divided by 3 times my box length. This is a cool fact, since if you remember that work equals force times distance, then it makes sense that an energy value divided by a distance would give me a force. Now, let's plug that back in to the pressure equation from the very beginning. So now, we get this kinetic energy relationship to the pressure. It looks very crowded, so let's see if we can simplify it. Already, we can see that the volume of a cube is just d times a, so we can replace the denominator with 3v. Now, remember that the number of particles n is defined as Avogadro equation for moles. So we can sub in the number of moles n times Avogadro's number. Now, we are getting very close to another famous equation. If we move over the volume to the other side, we have PV equals 2/3 of n times Avogadro's numbers times the time averaged kinetic energy. We remember that PV equals nRT is another equation we learned that came from empirical facts about ideal gases. Well, by comparison, we can write that Avogadro's number times 2/3 times the time average kinetic energy must be equal to the gas constant R times T. This is where Boltzmann came up with his miraculous constant. He stated that the gas constant must be hiding the link between the micro and macro world. So R must be equal to Avogadro's number times some constant that we now call the Boltzmann constant in his honor. Knowing this, we can cancel the Avogadro's number and change R into the Boltzmann constant. We now end at the revolutionary result that the time averaged kinetic energy is 3/2 times the Boltzmann constant times temperature. This is so important to the physics and chemistry world that we put it on a pedestal since it is the main relationship between how energy is transferred from small molecules to something on the macroscopic scale, such as temperature. Notice how the Boltzmann constant is very small, on the order of 10 to the negative 23. This makes sense since Avogadro's number, which represents the number of molecules in an object that we can see, has the same order of magnitude in terms of value. This is the key to thermodynamics and a beautiful example of what is to come in the class. Please commit this idea to memory. As my thermodynamics professor, Dr. Griffin, once said, I want you to be able to wake up in the middle of the night and remember that temperature is just the average kinetic energy of molecules bouncing around, and that the Boltzmann constant tells us this relationship. See you all in class.